Good evening, guys. I hope everyone's well, and I hope everyone's keen to do some physics. Tonight I'll be answering questions 27 and 28 of the 2017 HSC Physics paper. Question 27 asks, the diagram shows an electric circuit in a magnetic field directed into the page. The graph shows how the flux through the conductive loop changes over a period of 12 seconds. So things to remember here are the definitions for flux, magnetic flux, and magnetic field. So magnetic flux is defined as the number of field lines passing through an area. It can be an imaginary area. A magnetic field B is the magnetic flux per area, or the magnetic flux density. So magnetic field line is represented by each of these crosses, where each one of those magnetic field lines is going into the page. The more of those crosses that we have inside this circle, the greater the magnetic field density, the magnetic flux density inside this circle or inside this area, and hence the greater magnetic field in this area. Okay? So, don't actually need that diagram there, so I won't have that there. I just wanted to explain what that's about. So, this question asks, calculate the maximum magnetic field strength within the stationary loop during the 12-second interval. Because magnetic field strength is just a measure of how dense the magnetic field lines are, that means we want the maximum flux in the area of the circle. So the formula for magnetic field strength in terms of flux is given by the formula B equals phi over A, where phi is the flux and A is the area of the shape. So the maximum flux is 0.6 Webers. So we can say phi equals 0.6 Webers. And the area of a circle is given by pi r squared, which in this case equals pi times half of the diameter squared, which is 0.3 squared, which equals 0.28 meters if I plug that in a calculator. Cool. Now, if I want to find my maximum magnetic field strength, which is when flux is equal to 0.6 Webers, we get Bmax equals 0.6 Webers over 0.28 meters squared, which equals 2.12 Tesla. So the maximum magnetic field strength through the coil, through that circular coil, is 2.12 Tesla. Cool. Question B asks, calculate the maximum voltage generated in the circuit by the change in flux. In your answer, indicate the polarity of the terminals P and Q when this occurs. So, we have a current, or we have a voltage that's generated within that circuit when we have change in flux. Whenever you have the amount of flux changing through a coil, in that case, that generates an electromotive force known as EMF. So, in this case, what we have, if we draw this situation, we have a coil, kind of shaped like this, and we have a magnet above the coil. Yep, so north and south. Now, since the magnetic field is going into the page, we can say that it's a north magnet that's directly above the coil. Now, of course, these magnetic field lines form closed loops that loop back to the south pole, but these are large loops in this case, and then it's going to take a while before it's not going to reach around to the south pole in this diagram, but that is what they are doing. Now, before we say what's happening to the magnet, we have to analyze what's happening. To calculate the maximum voltage, or the maximum EMF, we have to remember that the formula for EMF is given by E is equal to negative delta phi over delta T. So that means the change in flux divided by the change in time. If delta T is very small, that will make E very large. And delta T, and if delta phi is very large than phi, then E will also be very large. So we're looking for the point that has the shortest time, or the smallest change in time, and the largest change in flux. Now, looking at this graph, both changes are between 0.6 and 0 Webers for flux, but the changes in time are between 0 and 6 seconds and 10 and 12 seconds. So 10 and 12 seconds is our best bet. So E is equal to negative, and I'll write it here I suppose, I'll say delta phi equals 0 minus 0.6 Webers. Oh, and I'll say delta T, I suppose I'll put that there to make that accurate, equals 12 minus 10 seconds. Sorry, that took way too long. Okay, so that equals 0.6 divided by, so that equals negative 0.6, sorry, over 2 seconds. So we can say that E, because it's the negative of that fraction, is equal to negative of negative 0.6 over 2, which just equals 0.3 volts. So the maximum EMF is 0.3 volts, and it's positive. Now, the second part of that question asks, indicate the polarity of the terminals P and Q when this occurs. And this is not a straightforward answer, and this is what makes the probably large part of the marks in the question. Okay, so the first thing we note is that during the point of maximum EMF, the flux is decreasing. That means in our situation, in this diagram that we've drawn down here, or that I've drawn, I should say, the magnet is being pulled away. Now, when we have a current that's induced in a coil because of a change in flux, the current that is induced in that coil acts in a way that it produces a magnetic field that opposes that change. And that's called Lenz's law. So the coil is always trying to oppose the change in flux in the environment or through the coil. So in this case, what happens is this coil is trying to resist the motion of this magnet. It's trying to stop it from being pulled away. So what it does is it sets up its own magnetic field by inducing a current in its own coil. Now, if it does have a magnetic field, it's going to have a magnet such that this is a south pole and this is a north pole. And you can imagine that this magnet is in the middle of the coil. I've just drawn it out here for clarity. So the magnet is in the middle of the coil, and it has a field where such that the south pole is facing towards the north pole of the receding magnet, if it was there. Now, what that means is that there is a magnetic field that is pointing downwards through the middle of the coil. So this one's actually originating in the coil. Maybe I'll draw this in a different color. Yep. Draw it in black. So this is the field that's being induced by the coil. So the north pole is pointing down. Now if we use the right hand screw rule, and everyone's able to do that, imagine you have a screw. Imagine you have a screwdriver and you're using it to screw a screw down the page. And if you wanted to push that screw down the page, you would have to be turning it clockwise. You would have to be turning that screwdriver clockwise. And in that case, what just happened there? I don't know. Somehow I did that. Oh no. Okay, so we've got a magnetic field like that. And we have a current that's induced in the coil that looks like this. So that's going clockwise. Cool. Now, we need to know, so we now know that our current in the coil is going clockwise, but we need to know the polarity of the terminals, P and Q, when this occurs. So we have a voltmeter that's located here, and it's located inside the circuit. We have a point P, and we have a point Q in here. We have to know the polarity at this point. So because a conventional current is the direction a positive charge would flow, we can say that positive charges are building up at P, and as a result, the negative charges would be building up at Q. So the polarity of P is positive, and the polarity of Q is negative. Okay. Question 28. Contrast the design of transformers and magnetic braking systems in terms of the effects that eddy currents have in these devices. Okay, first of all, here's just the answer that I wrote for it. Keep in mind, it's a 6-mark question, so we want to be really talking about the purpose of each of the devices, and we want to be talking about how they're different. So, transformers are designed to transform voltages between two electrically isolated coils wound around an iron core. Ideally, they do this with no energy losses, but the iron core, which maximizes the magnetic flux, is also conductive, and eddy currents that produce waste heat are generated in the core. To reduce these effects, the core is laminated to reduce the size of the eddy currents. Magnetic brakes, on the other hand, are designed to reduce the kinetic energy of something, usually a train. The goal is to maximize energy losses, so the brakes maximize eddy currents using non-ferromagnetic conductive materials like copper. Now, that's probably enough for that 6-mark question, but just to add a bit of extra understanding to it, you could draw some diagrams too. You don't have to do that though, but just to make sure everyone understands what I'm talking about. In a transformer, we have a setup that looks kind of like this, where we have the primary coil, and we have the secondary coil. This is a step-down transformer because we have less coils in the secondary side. So, and this center block is made out of iron. Now, because it's conductive, it can actually, so eddy currents get set up in it, and those eddy currents take some of the energy away from that secondary coil. Ideally, there'd be no eddy currents being formed, and all of the energy that's being output by the primary coil will be picked up by the secondary coil. But that's not the case in reality, unfortunately. To reduce this effect, the iron core is set up in sheets with laminated sheets, or with little laminated areas between them. And it kind of looks something like this. So imagine if we took a top-down view of this, of our transformer. Then this is actually separated into very thin sheets and the lines that I'm drawing here represent little areas of laminate which separate the sheets of iron. So that in between, so that the layers of iron are pretty thin, and only very small eddy currents can form inside them, and that reduces the energy losses basically. Cool. So, just to sum that up again, transformers are trying to reduce energy losses, magnetic brakes are trying to maximize those energy losses. Cool. So guys, that's been questions 27 and 28 of the 2017 HSC Physics paper. If you liked this video, please give it a thumbs up. If you disliked it, give it a thumbs down. And if you do that, make sure you leave a comment in the comment section below, just so I know what you disliked about the video and how I can work to improve it in the future. Okay, thanks guys, and have a good night.